Okay guys, let's do more applications for 13.7. Find the point or points on the surface of the shape defined by the equation z equals 3x squared plus 2y squared minus 3x plus 4y minus 5, where the tangent plane is horizontal. Now, if the tangent plane is horizontal, what does that mean? It means that this whole thing is equal to 0. Namely, all of my partial derivatives need in the x and y direction is 0, because then the normal can be either vertical or horizontal. So I need my x partial to be 0 and my y partial to be 0, because the plane can neither go left or right, or the plane needs to go fully left and right, or in the x and y direction. Okay, so let's move our z over first. Now, what is my x partial derivative? 6x minus 3. My y partial derivative, 4y plus 4. Suppose those equal to 0. So x is 3/6 or 1/2. Y would be -1. What's my z partial derivative? It's -1 here. So obviously that one could never be 0 anyway. So let's see, what is where is x 1/2 and y -1? Well, I have this function up here I can just plug it back into. So z equals 3 times 1/2 squared plus 2 times -1 squared minus 3 times 1/2 plus 4 times -1 minus 5. That's 3/4 plus 2 minus 3/2 minus 4 minus 5. Okay, let's see. 2 minus 4 minus 5 is -7. 3/4 minus 3/2 is -3/4. So that's -28/4 minus 3/4, which is -31/4. So that means the x value where this occurs is 1/2, the y value is -1, and the z that corresponds to it is -31/4. Doesn't seem like there's any extra positions. There's no z squared, and since x and y have to be fixed to those 2 points, we don't really have much choice. So there should only be 1 point, and it should be at 1/2, -1, -31/4. Okay, one last application here. In the past, we have generally found the angle between planes by using the normals. Well, the gradient is the normal, something normal. So another use of the gradient now is to determine the angle of inclination of the tangent plane to the surface. So we can look at a surface and figure out the angle of the tangent plane relative to normal. The angle of inclination is going to be between 0 and pi over 2, because the given plane, like the inclination would go back down after you reach 90 degrees. Because the vector k is normal to the xy plane, you can use the formula for cosine of the angle between 2 planes to conclude the angle of inclination of a plane with normal vector n is the cosine theta equals the absolute value of the dot product of n and k divided by the magnitude of n times the magnitude of k. Now, if k is just a unit vector, then the magnitude of a unit vector is 1, so all we have to do is divide it by just the magnitude of n. Okay, so let's do a problem with this. Find the angle of inclination of the tangent plane to the ellipsoid defined by x squared over 12 plus y squared over 12 plus z squared over 3 equals 1 at the point 2, 2, 1. Okay, so let's find our partials so we can get the gradient. That's x over 6. The y partial is y over 6. The z partial is 2z over 3. This is at the point 2, 2, 1. Okay, so at 2, 2, 1, we get 2, 6, or 1/3. This is also 1/3, and this one is 2/3. So we get the gradient is 1/3 I plus 1/3 j plus 2/3 k. Now recall, we need the dot product of that with k at 2, 2, 1. Now k is just the vector k in the k direction, which is the vector, remember I is in the x direction, j is in the y direction, so k is in the z direction. If it's a unit vector in the z direction, it has to be 0, 0, 1. So if I take this 1/3, 1/3, 2/3, the dot product of that with 0, 0, 1, it becomes clear that the only thing that survives here is the 2/3. So you have cosine theta equals the absolute value of that, so that's 2/3, over the magnitude of n. So the magnitude of n is the square root of 1/3 squared, which is 1/9, 1/3 squared, which is 1/9, 2/3 squared, which is 4/9. This is 2/3 over the square root of, looks like 6/9, which would be the square root that reduces to 2/3. So it looks like this would be 2√3 over 3√2 if we flip this fraction. So that means we have to take the inverse, the cosine inverse of 2√3 over 3√2, and that would give us the angle of inclination. Now, little theorems here at the end. The gradient is normal to level curves. Again, we talked about that. The gradient is also normal to level surfaces. So when we get into more than just 2 dimensions, it's still normal. And that's all for 13.7.